Standing waves arise in many different situations. But essentially, a wave travelling in one direction, when it meets an identical wave travelling in the opposite direction, can overlap to establish a standing wave. The standing wave will have a number of interesting points, nodes where there's minimal displacement and antinodes where the displacement is maximal. This can be conveniently demonstrated with the following equipment. A milk frother, a little swivel that anglers commonly use to ensure that their spinner spins in the water when fishing, some elastic cord that can be easily stretched, and the fourth component in this case is some bath chain. So when the little frother is switched on, a vibration occurs that is transmitted through the elastic cord, as we shall see when my assistant holds one end of the cord for me. What we're witnessing formed effortlessly and reveals a standing wave with nodes and antinodes and patterns that vary depending upon how tightly stretched or slack the string is. The separation between the nodes is significant. It relates to the wavelength of the wave. Specifically, the separation between the two nearest nodes is 1/2 a wavelength. If now my assistant allows the chain to come in to operation, then when we switch on, we can see that the standing wave forms throughout the entire length, but that the separation between the nodes is closer in the chain and further apart in the elastic cord. This is very significant because what it reveals is that although the frequency of the wave was the same all the way through, the separation of the nodes being less in the bath chain is indicative that the wavelength is less, and therefore that the speed of the wave is different than it was in the elastic cord. That change in wave speed that occurs when waves pass from one medium to another is the very thing that accounts for refraction. And so that is one of the values of demonstrating standing waves with this particular combination of components.